So just coming back to the third revolution, because I've done this one. That was my first cell phone, because I'm born at almost the same time of the first wireless phone that was designed in the 70s, but really sold in the 80s. So I'm connected to that story there. And what I've done, this is my research work on how to put together what we have known in the 80s, all these features there, music, whatever, video, and so on, to fit it on a single smartphone. And of course, the question of power is at the center of everything. So it's how to integrate all these schematics of function or feature into small dice to go on the smartphone. But what we have to fight against is ourselves, our usage of technology. Here is just the curve on how many photos that are exchanged. I think it's per year, but it could be per month. I forget that. And you can see it's thousands of billions of pictures. I've seen some of you have taken pictures. Rodney have taken a picture, I know, 1 hour ago in the front of the lab. It's already on the internet. There is a cost for that. Wireless communication. So what we see is that 95% of the data are exchanged wirelessly. They go through that. It's huge. It was not like that a decade ago. And how we have to mitigate with that is to have very complex transceivers. Here is the one published by SSCC 5 years ago, for the first one for 5G. You can see the number of receivers, transmitter to accommodate that. But at the same time, we have the technology that can fit billions, I mean tens of billions, maybe hundreds of billions, soon of transistor on a single die. And in France, especially, well, I would say in Europe, we have ST Microelectronics to do that. But, well, all this together, and saying we come back to that question of power, if we go for our 6G network using the actual architecture, we need to cover the image lens twice on Earth with solar panels just to power that. It's just impossible. So we need to find solutions for that. And you know, Greta Thunberg, she's not happy when it's about CO2. So yeah, what are we going to do? For 6G, well, what can we connect more than ourselves and so on? This is the trends. It was from 5 years ago. There are other things to connect. Robots. Have you heard about, well, sorry to say the name, but Elon Musk and his humanoid robots that already worked? We need to connect those robots, and they will ask a lot of data to exchange, to coordinate, to act together. But then after that, we have what we call the sensing intelligence and hybridation with human. Maybe in a future, we can have a chip in the head or whatever, and to have the telepathy, and which is a lot of data. The bottleneck is still there, and this is what we have at the first presentation. It's always the data conversion. And in a mobile phone, boom, you have to deal with many constraints: speed, resolution, integration, consumption, and the top of it, standard. So what we did, and I'm going to present the project, European project we are working on, is how we can reduce that power. Here you have two images with dots. Each dot is the same power consumption that will impact in terms of power consumption. So which one has the lowest number of dots? Of course, second picture. But it's the same information you are viewing there. One in the time domain, the other one in the frequency domain. So we should convert in the frequency domain and not in the time domain if we want to reduce the power. So we question ourselves, can we design a transceiver to convert information in the frequency domain directly? And when it's about frequency, you know that very famous French guy about frequency transform from Grenoble. Yes, that's true. It's Joseph Fourier. Joseph Fourier, the Fourier transform. So that can do that. It's a complex operation, complex numbers, and it's difficult to integrate. There is a cost for that. You have a transform which is similar to Fourier transform. It's called the Walsh transform. It's a real one, but kind of digital. And when it's about digital, it's very easy to integrate. So let's use the Walsh transform. It's American. It's great. So we can see how we can put that together to make a transceiver. What you have here is the squares of the Walsh transform. And in fact, when you combine them, you weight them, you can generate any kind of waveform. Here, a sine wave for communication, modulated signal. So this is the transform we will integrate to perform that conversion. And in fact, Walsh inspired himself from Jacques Hadamard, who was associate professor here at the university, but in another century. So what we want to do is to use the most advanced technology, CMOS, of course, but CMOS is purely nonlinear. It's terrible, especially when it's very advanced node. Everything is nonlinear, so we need to deal with that. At the same time, we want to use our conversion, the Walsh transform for that. So what I have to deal with is here, what you have in blue, this is where I want to communicate. In red is the nonlinearities that will create some distortion of my signal I want to suppress. So there is a technique for that, which is called pre-distortion. We are going to pre-distort the signal, so at the end it will be linear. For instance, the PA is very non-linear. And here you have a log curve. So let's add at the entrance an exponential. Log of an exponential is something linear. So the question is easy. Can we do that in the Walsh domain, as I have my Walsh converters there, but using the mathematics of Walsh? And the answer, of course, is yes, we're going to try to do it. And to make everything linear, you don't have here the red potato on the two sides of the band, meaning that it's pure linear. So we have worked on that since 5 years. Here you have a few papers on how to make the converters and so on. But the fact is that it's a lot of information. With the correct algorithm, we can make it. But 6G, we think that it will not operate not only at the sub-6 gigahertz bands, but at sub-terahertz frequency, 150 gigahertz. So you can see here, it's Jean-Claude Van Damme. And I put that because we have room for tens of gigabits at those frequencies for our robots to communicate a lot of information. Short range, but a lot to communicate. So that means that we are going to use the transistor at this frequency. It will be even more nonlinear, more critical to design. So it's billions of data to make it work. And this is where we ask AI to help us. You know that AI is not perfect, but at least 95% is good to linearize, to operate the whole system. And thanks to René, because René is in charge of the project for that, with our friend from KU Leuven, we demonstrated that we can achieve the communications thanks to AI using CMOS technology. So even with the worst technology, we can do something quite the best. Tens of gigabits sub-terahertz in CMOS thanks to Walsh. So you have that recipe, you combine them, and you have the Hermes project. This is the overview of the transceiver we've designed. We process the signal in the Walsh domain, we convert them, we go at 150 gigahertz, and we have AI on the top to manage the modulation, the spectrum, to correct all that. Seems magical, but that's a lot of work, as we have designed all these parts during 5 years. And what you have here is the 3 parts. Walsh conversion, we have designed the 2 converters. 2 of them are state-of-the-art. The lowest power consumption for the DAC, and as you can see here, the Boris-Merman curve, we are just a little bit out of the limits. That was impressive. I didn't expect that result in the project thanks to Walsh. AI, same demonstrated that we can reduce the power consumption of that linearization by a ratio of 5. It was even more. I was thinking 3. It was 5 at the end, so that was great. And up to 20 times for just the DPD of the power amplifier. Outstanding. In CMOS technology, this is what Antoine is going to present after. We had some electronics now to perform almost state-of-the-art performance in CMOS technology for 150 gigahertz. So guess who is happy? Greta Thunberg is happy because we've done it. And it's a good experience. So you can see René somewhere there in the picture. I think, yeah, he's part of the project. So we take pictures. That project, in fact, involved 30 to 40 people, which was great. And at the end, my picture of the architecture changed. You can see circuits there and the figures we've obtained. So for conclusion, Why? Let's connect the intelligence. AI is here in that project in our transceiver to improve the electronics and manage the spectrum. It speaks in the Welsh language, so not the time one, but the frequency one, and it fully operates the radio. Yes, that's fun. AI has its own hardware to communicate. But, well, I thought about that, said, yeah, if I give to AI hardware to communicate, that's good for us, human-to-human communication, human to machine, machine to machine, but maybe at a given time, machine to human, and I don't know what's going to happen. It's pure science fiction, and it might come science reality. Thank you very much. Question. Time for one short question. If no, that's fine.
It's a very simple question. Over all the technology and this mentioned in the presentation, I missed the quantum computing. What are your thoughts on quantum computing and how can be integrated with AI and the 6G?
Yes, I think the combo of AI and quantum computing will give another scale of performance. I don't know about the state of the art of that, because it's changing to have a chip operating as close as possible to the qubits, at 4K, for instance, and especially signal processing would dissipate power, which is not compatible with the crystal. But if AI was performing, had the quantum signal processing capabilities, I think, I can't imagine how powerful it could be, but outstanding, I think. Yes.
Okay, so thank you again. Okay, so now our next speaker, the PhD student Antoine Lhomel, that will present from the University of Bordeaux, that will present us a circuit-level design for intelligent system key challenges.
Thank you, Maxime. Good afternoon, everyone. So this work has been made at the IMS laboratory under the supervision of Professor Nathalie Deltemple and Dr. François Rivet. The overview of the presentation is the following one. So we will first talk and make the following of the previous presentation about the Hermes project and go a little bit deeper inside the circuits. So as François has presented just before, the 6G overview tried to aim the sub-terahertz spectrum and especially the D-band around 110 to 170 gigahertz to achieve high amount of data, wide bandwidth, and high carrier frequency. If we are looking at the Hermes project, here is the full project, but we are going to focus especially on the RFFE and more precisely on the PA and try to solve the challenges linked to these circuits. So if we are looking a little bit at the state of the art, and we are targeting mainly two technology. The first one is the CMOS technology, and the second one the CD technology, because it's the most, the less cost-effective technology, and we can achieve high power gain and an output saturation power around 15 to 16 dBm, which can be quite good in order to target 6G application. But if we are looking at the power amplifier, what are the challenges that we are facing with this kind of technologies? So there are four of them. The first one is to work with high RF performances transistor, which means we need to have IFT and Fmax. The second one is to achieve enough power gain, because if we are working near the maximum frequency of the transistors, we have low power gain, which is quite embarrassing for a power amplifier. The next one is to have enough output power and efficiency to meet the standard requirements. And at least we need to have a high accuracy because we are working at high frequency, up to 150 gigahertz. So we need to be really precise on the modelization of both actives and passive components. So to do so, we propose to work on a 4-stage PA, which is this one, and we'll try to explain what we have done around the transistor to meet all the challenges described just before. So we are using two gain enhancement techniques. The first one is the dual peak gain boosting, and the second one, the neutralization. I will go a little bit into detail just after. And also on the passive part, we are trying to develop particular transformers in order to achieve the wideband required by the project and for maybe the next 6G standard. To do so, we have this circuit, so a differential pair that we are going to use a positive feedback network composed by the C1, C2, L1 components, and the purpose is to improve the gain around the transistor. We are going from low power gain around the transistor, which are a little bit higher thanks to this network. We need to be really careful because as we are working with positive feedbacks, oscillations are not far away, and we need to be really aware of this problem. The second gain enhancement method we are using on this PA is based on the neutralization. So the neutralization is a quite known technique for the PA designer, which are used for stability most of the time and for 4G or 5G application. But we are trying to take profit of that by increasing the gain. So we need a compromise between the gain and the stability. And to do so, the effect is quite the same because we are using the capacitors to improve the gain of the differential pair. But once again, we need to be careful on this because since we are not using the process variation of the transistor, we need to be careful because one movement can be on one side and the other on the other side, so we can have conflict after the fabrication of the circuit. To verify this hypothesis, this circuit has been sent to two manufacturers, and it has been designed in 28 nanometer FD-SOI from ST Microelectronics, which meets the requirement on IFT and Fmax for the transistors. And also, we have respected all the integration rule of the technology, which means that even if this circuit is manufactured, it can be reproducible and maybe try to have a large scale of integration. We have measured this circuit on two benches. The first one at IMS lab here in Bordeaux, and the second campaign has been made at Lille in order to cover all the band from 110 to 220 gigahertz in order to fully characterize the circuit. The results are the following one. So we can see the comparison between the measurement on both bench and the retro simulation, which have been made after the measurement, in order to show that we can achieve high power gain, which is one of the challenge for the PA. We are achieving a gain of 20 dB after measurement. So we are at the state of the art for the power gain in the CMOS technology, but we can see there is still improvement, especially on the bandwidth improvement and most of the time on simulation, because we need more precision to really take into account all the behavior of the circuits. The other parameters that we need to check is that if we want to have a commercial application for 6G, we need to show that our process is reproducible, and on a less lower number of chips, we are trying to show that even if we are measuring many chips, we can achieve most of the time the same results, which is first a good thing, because even if the circuit is made with particular positive feedback, we can reproduce it on multiple chips, and we can expect that this behavior can be used on thousands or billion of chips. And we also are more confident on the measurement because we have made the measurement on 4 chips, and 4 times we have almost the same result. So that's for the small signal parameters. Now, if we are looking at the large signal parameters, here is the characterization made at 132 and 145. So we can see that for both bench, once again, the measurements are reproducible, but we are lacking of output power and efficiency, which are the two main problems on these structures, and we are trying to solve it for the next improvement on the technology. Also, we have tried to characterize this PA with modulated signal measurement, because even if we are trying on continuous wave measurement, this is far away from reality, and we need to use modulated signal measurement. So that's why we have made a measurement using a 16-QAM modulation with 2 data rates. The first one at 20 gigabit per second, and the second one at 44 gigabit per second. And we have characterized the EVM of the PA. We have identified 3 areas of use. The first one, when we are low input power, the SNR of the PI is degrading the EVM, so this area is not quite good for operating the PA. The second one, where the EVM introduced by the PI is not really higher than the one of the full system used for the characterization, which is quite good to use if we are using the modulation. And the last one, which is also an area of degradation due to the saturation of the PA and the introduction of the nonlinearities. These scenarios also show that we can measure high data rates on the PA and it's working. So that's quite encouraging for the following of the project. Now, since we have made a circuit, we need to compare it with the state of the art, which is the purpose of this slide. We have tried to take all the main parameters of the PA and trying to compare it with the figure of merit, which is the figure for comparing architectures. We can see that for the first one, which is the classical one used for the PA, we are a little bit lower, which is quite normal because we do not have power combinations. We are lacking of this large signal parameter and especially the output power. But on the second one, which is more used for subterranean PA and most for the boosted PA, we are quite good and we are one of the best FOMC in state of the art because we have achieved high power gain for low power consumption, which is quite good for the 6G application that we are targeting. To conclude on this presentation, so we have developed a methodology for D-band design and especially for the PA, which enabling a safe design space for the power amplifier on millimeter wave, integrated the gain enhancement method. We have manufactured this PA and measure it. We are achieving one of the best FOM targeting the gain and the power consumption seen in the state of the art, and we also showcase the potential of the technology by showing the repeatability of the measurement first on the chip and also on the setup. But as I said, the last improvement we need is the increase of the output power, which is the main problem of these architectures. And to do so, we have proposed a second architecture sent to manufacture in October 2024, which is a combined architecture using a T-junction combiner. And this architecture is mostly designed like the first one. So we are using the gain enhancement method that we have shown are working really well on the PA. And we are trying to take the benefits of this method and integrate it with the power combination to achieve all the requirements first for the project and also for the 6G application. Thank you very much for your attention.
Maybe one short question.
Yes.
I'm wondering why you are using the FTSOI technology for design?
For two main things. The first one is that it's the technology with IFT and Fmax, which is the most the main requirement, I would say, for this kind of technology for D-band design. And the second one is that in the case of the project, we are trying to co-integrate multiple blocks, so the front end on the first part, and also the analog to digital conversion on digital to analog part. And this part, especially, really take benefits of the 28 nanometer FD-SOI. So it's not maybe the technology with the highest RF performances we can have, but it's the best compromise between co-integration and possibility for D-band design. We are limited in terms of power, but we can try to find other solutions like maybe power combination and trying to play more on the passive parts of the circuit design instead of the active parts and trying to reduce as much as possible the losses, playing on power combination to try to have the highest power we can have for the PA. That's the compromise. So we need to take care of first the transistors. We need to take care of the components and passive components part, and we are trying to find a good compromise between sizing the transistor for enough output power and trying to reduce the chip area. So yeah, it's the compromise first between analog and digital part, and also on the chip trying to play with the area to make it as small as possible to have enough output power at the end of the day.
So it's quite hard to compile with people to compile with others.
Yes.
Processes. Thank you, Rob.
Thank you.
No other question? Thank you again.